Let's take a look at how to solve one of these problems using energy, wavelength, photons, and light. The first part of this question is asking us to solve what is the energy in joules released when we move from energy level 5. So we're starting out at level 5 and we're jumping down to energy level 2. Now when we go from a high energy level to a low energy level, what happens is light gets released to take care of that transition in energy. 5's high energy, 2 is lower energy. When we jump down, the energy has to go somewhere. It gets released from the atom as the electron jumps down in the form of light energy. When one electron makes one hop, it releases one photon of light. The equation that would be appropriate for solving this particular problem would be the one that connects energy with energy level high and energy level low. Now in this case, energy level high, or N high, would be 5, so this would end up being, we would have 1 over 5 squared, and our low energy, the level that we jump down to, is 2, so it would be 1 over 2 squared. Now if we include with this then the value of the Rydberg constant, we end up with our equation of energy is the negative Rydberg constant times 1 over the n value high squared minus 1 over n value low squared. And we end up with energy is equal to, our energy would be equal to negative Rydberg constant times 0.04 minus 0.25, and ultimately this gives us an energy of 4.578 times 10 to the negative 19th joules. This amount of energy would represent the energy of a single photon of light released when an electron jumps from level 5 all the way down to level 1, and in so doing jump from 5 down to level 2 and releases some light energy. This would be the amount from one electron making one jump, the energy in a single photon of light released. The next part asks us to now convert the energy in the photon to the frequency of light. This can be figured out using E equals h nu. We now know the energy from part A. H is Planck's constant, frequency would be the nu. Let's rearrange this so that we have energy divided by Planck's constant gives us the frequency. What we now have is the energy from problem A, 4.578 times 10 to the negative 19th joules, divided by Planck's constant, will give us the frequency of this particular light, and the frequency comes out to be 6.909 times 10 to the 14th, and it's hertz, or also called reciprocal seconds. What that is, it's that many cycles or wave crests that would pass a fixed point in a single second of time. So this would represent the frequency of light that we have given off when we jump from level 5 to level 2. Part C then asks us to now convert the frequency into a wavelength. Now for all types of wave energy, the speed is always equal to the frequency times the wavelength. Whether it's a sound wave, a light wave, a water wave, all waves follow this particular relationship. For our purposes with light then, that's going to be the speed of light is equal to the frequency times the wavelength. Let's rearrange this to solve for wavelength, so we have the speed of light over the frequency will give us the wavelength of this light. Now the speed of light is provided, its unit of measure is meters per second. Frequency is in reciprocal seconds. The seconds cancel out because the speed of light is in terms of meters. When we get an answer for this setup, our wavelength of light will be in terms of meters. The wavelength represented by this type of light, representing light given off from a level 5 to 2 transition of an electron, would be 4.339 times 10 to the negative 7 meters. Now, one thing, light is often expressed in terms of nanometers, so you would need to know how to convert between meters and also nanometers, or from nanometers to meters. To do that conversion, we just have to do a proportion. The proportion that we can set up uses the conversion for nanometers to meters. A nanometer is 1/1000th of a meter, so we know that 1 nanometer is present in 1 times 10 to the negative 9th meters. Therefore, x nanometers would be present in 4.339 times 10 to the negative 7th meters. When we solve for x, we arrive at 433.9 nanometers would be our wavelength of light for this particular transition from level 5 to level 2. Let's now take a look at a different type of problem. Here we start out with, instead of finishing with the wavelength as the previous problem, we start with the wavelength. We're given that green light has a wavelength of 510 nanometers. Because the speed of light that we'll be using later in the problem is in terms of meters, before we go forward with the calculation, we need to switch the nanometers to meters. We can once again use our proportion that we used a moment ago. The proportion we would use, once again, uses the relationship of, we know because a nanometer is 1/1000th of a meter, there's 1 times 10 to the negative 9th meters per 1 nanometer. And using a proportion, then, we can find there's x meters present in 510 nanometers. When we solve for x, we find our wavelength in terms of meters is 5.10 times 10 to the negative 7th meters. This would now be appropriate to use in subsequent calculations where the unit needs to be in terms of meters for our wavelength. Part B asks us to now switch the wavelength, which we've put into meters, into frequency. And again, the speed of any type of wave is always equal to its frequency times the wavelength. We now know our wavelength, we know the speed of light, so we can rearrange this to speed of light divided by wavelength will give us our frequency for the light. Now in our setup, the reason we had to switch the wavelength of the light to meters is because the speed of light isn't also in terms of meters per second. The units need to be consistent within a calculation. Using this setup of speed of light divided by wavelength gives us our frequency. We find that the frequency for this light is 5.878 times 10 to the 14th. And again, this is in terms of reciprocal seconds, or cycles per second of this light. Part C of the problem asks us to now find the energy of a single photon of light that has this particular wavelength and frequency that we found in parts A and B of the problem. Since we now know the frequency, we can use this equation, E equals h nu, that relates energy to the frequency of light. Let's rearrange this. Oh, we don't need to rearrange this. We have energy. It's going to be Planck's constant. Our energy for this single photon of light can then be given by Planck's constant times our frequency of light that we just found. Solving for the energy of a single photon of light that has this particular frequency and wavelength, we end up with an energy of 3.895 times 10 to the negative 19th joules. The last part of this question asks us to now find the energy that would be released if not a single photon of light was released, but an entire mole of photons of light is released. This we can solve using a proportion. We now know that we have 3.895 times 10 to the negative 19th joules are released per 1 photon, which means we would get x joules being released if we released a mole of photons. A mole of photons would be Avogadro's number, 6.02 times 10 to the 23rd. Photons of light energy would represent 1 mole of photons being released. From this proportion, we can get the energy released by a mole of photons of light would be 2.344 times 10 to the 5th joules of light energy per 1 mole of photons.